Um, okay, before I get going today, what is happening here? Okay, let's see. Um, so there's no class on Tuesday. Um, or office hours. Um, and so instead, I'm going to do 4 hours of office hours on Wednesday. Um, I was thinking of just doing 10 to 12 and 1 to 3 again, like I do on Tuesdays. Does that seem like good for people? Anybody have any other suggestions or other needs for that time? Okay. Uh, so this is next Tuesday is the 21st. So I'll do 4. And I'm going to be here and I'm going to give a Zoom link so you can do it remotely or come in. Um, um, so that is 7:22. Um, so this will be Zoom and in person. And then exam 2 is going to be next Thursday. So that'll be 7:23. And I'll be checking messages and emails and stuff. So let me know if you have questions too. I'll try to get back to you as soon as I can. Okay. So the first thing what I want to do today is talk about the test, and I'm going to go through all the test questions. Um, and then I want to take any questions you have on homework, go over any problems you'd like me to go over on the homework, and then we'll go through a bunch of example problems. Um, so exam 1, um, basically overall the scores were lower than I would expect on this. Um, these are lower than usual. Um, it seemed like what I saw most often was just people not putting in the time to absorb these methods as well as you should. Um, you really can't just think your way through this stuff. I'm giving you methods that are going to work for these problems, and what you need to do is just keep doing these problems and doing these problems and comparing to your answers to the solutions until they match, basically. Um, and so I'm going to go through the exam problems. I'm going to do it in the method that I prefer. I mean, there are other ways to do it, but you can't just think your way through it. You need to follow some kind of method, and so you might as well follow mine. I'm the methods I'm giving you are specifically designed to get you ready to do the kind of problems I'm going to give you. Okay. So as far as the scores themselves, that doesn't matter. Your fourth exam score can replace your lowest score, so this doesn't even have to be. But this, if you got a score that you're not happy with, and you can just calculate the fraction and see what your percentage is and see how it compares to the grade scale. But if your score was lower than you would like, that just means that what you did in that first week, you need to do something different. And what I saw most often was what you need to do different is compare your answers to the way I'm doing things and make sure you're doing it the same way. I saw a lot of solutions that didn't have free body diagrams. I saw a lot of people trying to do things component by component instead of writing out vector equations. All that stuff, you know, it worked in Physics 1 because, that class tends to be a little less vectory than later engineering classes. But, there's a point where you're shooting yourself in the foot trying to stick to the way of doing things that you're used to. Just move on to this method and you'll be happy. Okay. So exam 1, number 1. Well, let me pull these up. So number 1 is just a straight vector question. We want to find two unit vectors that are perpendicular to both of these. The cross product always gives you two vectors that are perpendicular to both of those, but the cross product itself isn't going to be a unit vector. In order to be a unit vector, you have to divide by the length. So we have 1, 0, 6 crossed with -3, 2, -1. And so that is 0, -12. And then for the y component, -1 minus -18. And then for the z component, 2 minus 0. And so you get -12, -17, 2. And then, well, I'll calculate the unit vector in this direction, and then the two unit vectors perpendicular to both of these are this and the opposite. So also, a lot of people just did the arithmetic of the cross product, got the wrong answer. Your calculators will do this calculation for you. I mean, I'd highly recommend just if you have a TI 84, 86, I would recommend entering the program that's given in that statics textbook, and it'll just always do it for you. You never have to do it by hand. If you have an 89 or an Inspire, that product is in there, cross P. Okay, so the unit vector in this direction is negative 0.574, negative 0.813, 0.096. We want the 2, so it would be like plus and minus this. So the other one would be, I guess I'll write it out, would be the signs of each one of these components switched. So 0.574, 0.813, negative 0.096. So that's for part A. And then for part B, we just want one vector that's perpendicular to both of these with a magnitude of 0.2. So we can multiply 0.2 by either one of these unit vectors. The key thing is you need to multiply it by the unit vector. This thing has a length that's not 1. It's not a unit vector. So if you multiply by 0.2, it has a length that's not 0.2. Okay, so get the unit vector and then multiply. And you get plus or minus negative 0.115, negative 0.163, 0.019. So that's number 1. Number 2, we have these 2 ball things connected by a cable. And we're given the coordinates of the 2 points. So this point here has coordinates. This is just in 2D. This is just x and y coordinates. Negative 5, 1.5. And the coordinates at the point B are 6, negative 2. And we want to calculate the force vector applied to A if the tension in the cable is 100, and then the force vector applied to B if the cable tension is some unknown T. All right, so for part A, a cable force is parallel to the cable away from the body. So, this way. And so in order to calculate the unit vector in that direction, because we want the unit vector in that direction so we can multiply it by 100, we're going to go B, the destination, minus the starting point. So we're going to go, our starting vector is going to be 6, negative 2, minus negative 5, 1.5. So that's 11, and then negative 3.5. And if you think about the direction of that vector, it makes sense with the way that arrow is drawn. It's in the positive x direction and the negative y direction. And then a unit vector in that direction, divide by the magnitude. And you get 0.953, negative 0.303. And so the force vector that we're looking for here, it says that the tension is 100, so it's just going to be this multiplied by 100. So that's 95.29, negative 30.32. And this is in newtons. By the way, about rounding, I don't care about rounding. I'm just checking to see that you do the steps right. So however you want to round it is fine with me. I know your chemistry professors will make enough of a big deal about significant figures that I can ignore it. And then for part B, so now we want, so the cable tension now is going to be T instead of 100. The other difference is we want the force vector applied to B by the cable, not to A. So this time our force vector is going to be in the other direction. It's still parallel to the cable, but away from the body. And so our vector this time is going to be, well, if we're sort of starting from scratch, the destination is that point A, -5, +1.5. The starting point is 6, -2. You also could recognize that this is just the opposite unit vector of the other one. And, you could skip some of this and just multiply the components by -1. So this gives you -11, +3.5. Yes?
So when we're reading the questions for this, is there like a good, easy to notice sign or marker to use the unit vector for the force for this? Or
yeah, so the idea of a unit vector is it lets you break up any vector into its magnitude times its direction. The direction is represented by the unit vector. So if you're told that you want something, you have to translate here that cable tension is the magnitude of that force. Okay, so yeah, tension is the magnitude of a force applied by a cable. And so so once you know that that's the magnitude, in order to come up with a vector that has that magnitude, you need to multiply that magnitude by a unit vector. Otherwise, you're multiplying by something with its own length, and that makes the length of the whole thing different. Okay. And then if you take the unit vector of this, you just get, what I just mentioned, you would get the opposite of the unit vector for the first part. So this is -0.953, +0.303. And if you think about the components, that makes sense for the vector I've drawn here. It's a big component in the -x direction, and a small component in the positive y direction. This one was a big component in the positive x direction and a small component in the negative y direction. And then the force vector, this time we're just going to multiply the unit vector by the variable t. So this is -0.953t, +0.303t. And that's it for number 2. Anybody have any questions about either of these yet? Okay, number 3. This is just dealing with coordinates and stuff, but it's in 3 dimensions. Okay, so we have our x going out of the page towards us, kind of diagonally. The y pointing to the right and z pointing up. And our origin is at A. So all we have to do is count take the distance along each of these coordinate axes. Think about whether it's in the positive or negative direction of that axis. This is the one that people in the class did the best on. Most people did this one right. So I'm just going to come up with the coordinates of these points. And I'm going to think of these coordinates as vectors because they are position vectors. They're vectors that go from the origin to the point. So B, we have to go, so from A, we don't have to move at all in the x direction. In the y direction, to get to B, we have to move 1 meter in the positive direction. And then now we're here, and we have to move 1 meter in the positive z direction. So there's B. Then the point C, starting at A, we have to move 2 meters in the positive x direction. And now we're here. We don't move at all in the y direction. And then we move 3 meters in the positive z direction. And then the last thing it asks is the vector going from B to C. So we're going to do this as the coordinates of C minus B. That's the destination minus the starting point. So that's 2, 0, 3 minus 0, 1, 1. And subtract the components, you get 2, negative 1, 2. And these are all in meters. So the units here are meters for that vector. Okay, so now we get into the two that are particle statics. The rest is all just kind of vector setup stuff. So we have this object, and we want to calculate the force vector applied to the 5 kilogram box by the cart, the force vector applied to the 10 kilogram cart by the table, and the normal force by the cable. I said table. The normal force applied to the cart by the incline. Okay. There's no order of things that you have to do, but in this class, the way you're going to want to approach it is you're going to want to do free body diagrams of each body and use Newton's second law. When we get into rigid bodies, you'll also use the moment equation, but use Newton's second law for each one of those bodies. So I'm going to just start with the 5. There's no reason that has to be the first one, but my free body diagram of the 5 kilogram we have a weight force that goes straight down. We have a 100 Newton force that's not straight down, it's perpendicular to the surface. And if you keep going around the boundary looking for contact, the only other place is the contact between the 5 and the 10. There's a friction contact. It says that in the problem between the 5 and the 10. And so a friction contact, you're always going to represent that as an unknown force vector. So it has components like this, and it doesn't matter what you call it. I'll call it R. And now we can write out Newton's second law. The two easy ones to write out are 0, negative 49.05. I'm not rotating the coordinate system or anything. I'm just, through this whole problem, I'm going to use like a standard coordinate system. And then we have Rx, Ry. That's two unknown components. And then the 100. What do we know about the 100? Well, you can imagine, like one way you can think of it is, imagine that this incline is on a hinge. You can rotate this incline. And imagine it starting flat and then rotating 30 degrees like this, okay? As you rotated it, that perpendicular force would start out vertical and then slowly turn this way 30 degrees. So that's one way to kind of reason it out. The way I like to do it is, I've done this in class at least one time before. It takes a while to get used to this way of doing things. But just go based on what you're given and just keep hopping around with the angles. And once you're in the vector direction that you want, then you can just add up all the angles. So what I'm going to do is I'm going to say, okay, first of all, we're given that a vector going this way makes a 30-degree angle with this. Okay, that's what the picture gives us. And then we want something perpendicular to that, facing down and to the left. So I'm going to now draw a vector like this. And what we know is that this angle is 90 degrees. Okay? And so now for my angle theta, from my counterclockwise angle from the positive x-axis, you can think about it a few different ways, but I'm going to go counterclockwise 180. Then I'm going to backtrack 30, clockwise 30. And then I'm going to go counterclockwise 90. And so what you get is 150 plus 90 is 240. The magnitude is 100. So this is 100 times the cosine of 240. 100 times the sine of 240. There's three forces in the free body diagram. I have three forces here, so I'm done. And I can rewrite this as, so we have, an x and a y equation. Rx, 100 times the cosine of 240 is negative 50 is equal to 0. And then we have negative 49.05 plus Ry. The sine of 240 is 0.866. Negative. And so this is minus 100 times that, which is 86.6. And so this vector R is equal to 50 in the x direction, and then 135.65 in the y direction, and this is in newtons. And that's one of the things it asks for, is the contact force applied to the 5 by the cart. That's what this is. So this is the answer to part A. Okay, now I'm going to draw a free body diagram of the cart, the 10 kilogram. We have the weight force down. That's 98.1. We have the cable force that's horizontal and has a magnitude of T. We don't know what that is yet. We have, since this is a frictionless contact between the incline and the wheels, we follow the rules of frictionless contact. So this is perpendicular to the surface toward the chosen body, and give that a variable name. I'll call it n. And then the last contact we have with the surroundings is the force applied to the 10 by the 5. Because this is, we can use Newton's third law here. If you're talking about a contact force between two bodies and you just switch which body you're talking about in that contact pair, it's the force on the other one just multiplied by -1. So this force, I'll write it the two ways you can think about it. So this is equal to -r. Yes?
If you had, just like theoretically speaking.
Yeah.
What if you had like A as like negative instead of positive?
Yeah, then that's fine. Then you write it. As positive A. Like if you had positive A, negative A in this one.
Yeah, like if you had like -50, -135.65.
Oh.
Just theoretically speaking.
Yeah.
Like, and then for the second problem, we had it the opposite sign.
Mm-hmm.
It's positive. Right. Like.
That's right. Yep. You always just whatever the components are, you multiply by -1.
Right. I'm saying like, what if like
if you had your coordinate system where the x and the y were in a different direction, basically.
Yeah, probably. I'm just like
Okay.
just throwing out.
Yeah.
Well, yeah. If then you would do this. But if your coordinate system is the one I've drawn, and you got -50, -135, then that's wrong, and your bridge falls down. But your bridge falls down if you build it like that. But if you do that in my class, you probably get 1 point off. So bridges are much
Less forgiving.
yes, much less forgiving.
So if we did the opposite coordinate system, we got it right still.
Oh yeah, for sure. If you did the opposite coordinate system, your numbers would all look different. But if they made sense in that coordinate system, then that's right. A lot of times in these tests, I'll specify a coordinate system so that I don't have to grade a million different, do this calculation in a bunch of different ways. But yeah, you pretty much always have freedom to choose your own coordinate system. In that sense, bridges are more forgiving. You always get to choose your own bridge coordinate system. In my class, sometimes I make you choose one. Okay, so this is -r, which means since this isn't usually the case, but in this case, we already know what r is. So I'm just going to write this as -50, -135.65. So Newton's second law now. There are three easy ones, and one where we have to think about a direction. T is just in the negative x direction, so -t0. -r here is -50, -135.65. The weight is 0, -98.1. And then that normal force. So again, maybe you can eyeball that. Think about that normal force again. Like if you think about that incline being on a hinge, started flat, that normal force would be straight up, and then rotate that incline 30 degrees. That would make that normal force go 30 degrees this way. And so we're at 60 degrees. You could also use in this case, it's kind of probably more complicated to think through doing the step-by-step thing, but it would go like this. So here's your coordinate system. What we're given from the picture is that this is 30 degrees. that normal force is 90 degrees this way. And so your angle is, I'll go counterclockwise 180. Then I'll backtrack 30 degrees clockwise. So that's negative. And then I'll backtrack another 90 degrees clockwise. And that comes out to be 60 degrees. So we have cosine of 60 degrees times n, sine of 60 degrees times n. That's all the forces. And so our two equations, the x equation says negative t minus 50 plus 0.5 n is equal to 0. The y equation says negative 135.65 minus 98.1 plus 0.866 n is equal to 0. And that's a system of two equations that you can solve by substitution, or it's easy to solve using reduced row echelon form. I'm going to show that again. This is going to be important for us later on when we get more variables in our systems. Okay, so we have two equations. Those are the two rows. We have two variables. I'll make that t and n. And then this is the constants. And remember that you have to move the constants to the other side of the equation from the variables. So we have, for t, we have a coefficient of negative 1. For n, we have a coefficient of positive 0.5. For a constant over on the other side, we have positive 50. And then for the second equation, for the t's, we have 0. For n's, we have 0.866. And get the constants over on the other side. And you get positive 233.75. And now if you solve this, you get, I'll just do this real quick. So we get T is equal to 84.96. N is equal to 269.92. Okay, that's almost the answer, but I asked for this in a very specific way. So what's the force vector applied to the 10 kilogram by the cable, first of all? We know the tension in the cable, but we want the force vector applied to the 10 by the cable. So you can go to Newton's second law for the 10 kilogram cable, and you know that that force vector is already written in here. And this is what we want. So now all we have to do is plug in our variable value for t, and we get that the force on the 10 by the cable is equal to negative 84.960. and the units are newtons. And then it asks for the normal force applied to the cart by the incline. Again, this is applied to the cart, so we'll go to Newton's second law for the cart. And the force we want this time is this one. And so the force on the 10 by the incline is equal to 269.92 times the cosine and sine is 60 degrees, which is 0.5, 0.866. And that is 134.96 to 33.75. Yes.
Suppose we didn't have like a calculator
Yeah.
to calculate like 3x3 or whatever.
Yeah.
Like, I mean, you give us 2 hours.
Yeah, right. Although, I mean, it would have been fine on this test, but in not too long, especially in this class, this accelerated schedule, in very much not too long, we're going to have big systems of equations that you won't want to try to do by hand, systems of 9 equations for 9 variables or whatever. You don't want to do that by substitution.
So you kind of expect us to know how to do it with a calculator?
Yeah. Mm-hmm. But it's easy. So, I mean, bring your calculator to me and I'll show you how to do it in 2 minutes, and it'll be useful in all your future classes.
I had to buy one.
Okay. Yeah.
I know how to do this.
Okay. Yeah.
And it's assumed like once you set up in the table that like then you're solving via the calculator.
Right. That's right. That's how I got from this to these 2 answers. Yep.
Making sure that that's the accepted.
Right. Yes, and so you don't have to write any steps in there. You don't have to know how to do reduced row echelon. I don't remember how to do reduced row echelon form.
Yeah, I mean, it's just a lot of operations.
Yes, yes. So I don't want to see those. That's the last thing I want to see.
Yeah.
I'll take points off if I see it.
Visual clarity.
Yeah, exactly. Any other questions about that one? Yes, question? No?
Well, it's a question about the different problem. So you said we can set our coordinate systems however we want, but I think you also said that we have to follow the right-hand rule, right?
That's true. Well, if you're doing 3-dimensional coordinate systems, your coordinate system has to follow the right-hand rule, where it has to follow x-axis crossed with y-axis equals z-axis. If you're only doing it in 2D, that doesn't really exactly come into it. It just means that your z-axis is into the page. If you put your x going to the left, yours is backwards for me. If your x is going to the left and your y is going up, that just means your z-axis has to be going into the page.
So what I noticed is that your problem actually didn't satisfy. At least I didn't think.
My problem right here,
The third problem.
number 3. Yeah, it does. If you so our x is this way, our y is this way. You don't have to write this. I'm going to erase this after I'm done, but it's like this. And so if you curl your fingers from start with x, curl your fingers to y, your thumb is in Z. It's a little easier to picture if you think of it as straight on. X is coming out towards you. Y is going over here, and Z is going up. So think of your fingers starting in the direction of X, curling until they're in the direction of Y, and what position your thumb puts your hand in. And remember the medallion. You can always make this medallion, and then you never have to try to use your hand again. It's cool looking too. It's a conversation starter at family reunions. Okay, and then the last one is the pulley problem. All right, so for my free body here, I'm going to take all of the cable underneath the pulley and the mass. So everything inside that red outline is going to be my free body. And so you don't have to draw the bat ears on it or whatever, but I think this makes it a little more clear what I'm including, because this doesn't work if you don't include that bit of cable underneath the pulley that goes under the pulley. So you have 490.5 here, and then you have a cable tension pulling on the excluded cable pulling on the included cable, and then same thing here in a different direction. And notice this angle is 70 degrees, and this angle is 70 degrees. So Newton's second law, so we can think of this as, well, it's 0, negative 40, 490.5, plus t times the cosine and sine of, this is 70 degrees from 180, so this is 110 degrees. Or, of course, you can always just draw out a right triangle and do the trigonometry and then adjust the signs by thinking of what quadrant you're in. That always works perfectly fine. This is just kind of a more algorithmic way to do it. And then the other one is t times cosine and sine of 70. And I'll rewrite this whole thing. You get, so 0, negative 490.5, plus, this is negative 0.342t, positive 0.940t. This one is positive 0.342t, positive 0.940t. it's equal to zeros. Now you can break it up into an x equation and a y equation. And you see that the components in the x equation cancel out, and you just get 0 equals 0, which, so that ends up being a useless equation. But the useful equation is the y equation that says negative 490.5 is equal to 1.880 t. Nope. Negative 490.5 plus this is equal to 0. So t is equal to 260.9 newtons. A cable can't push on things, it can only pull on things. And so when you draw your free body diagram according to the rules of cables, you're prescribing the direction that you know it is. So if you ever get a negative answer for a t value, something went wrong and you should go back and inspect what you did. Okay. This should always come out positive. Okay, so now we got that tension. That's our answer for part A. And now it asks for some force vectors. So the first one is, what's the force vector applied to the ceiling by the cable? Well, if this is the ceiling, the force applied by the cable to the ceiling is in this direction, where this angle is 70 degrees. And the magnitude is 260.9. So you can calculate that force as 260.9 times the cosine of negative 70, the sine of negative 70, so that is 89.23. To 45.25. Okay, so that, this should be negative. So I noticed that because I was just about to say we can check by, now look at that vector. What are the signs of the components? That vector, if its tail is at the origin, it would be in the fourth quadrant. So this would have a small positive x component and a bigger negative y component. If you calculated now the magnitude of this force vector, what would you get?
The 260.
Yep, exactly. So that's the idea that's the benefit of unit vectors. The magnitude of this is 260.9. It's just that it's in the direction 70 degrees below the horizontal. And now we have to do the same thing, but with the wall. This angle is 40 degrees. The magnitude is 260.9 because it's still the same cable. This angle is 40 degrees. So you can think of going, to find the angle for this, you could think of going counterclockwise 180 and then backtrack 40. So you get 140. And so this force vector is equal to 260.9 times the cosine and sine of 140. And so that is going to be negative 199.86, 167.7. Randomly using sig figs in a way that would enrage all chemistry professors. Any questions about that? Okay, so if you can find the time to do it, I really think it would be a good idea to, whatever questions, if any questions didn't go well on the exam, go back and try to think through it in the way that I do it in the lecture videos and in class and stuff. I think you'll find this just a really nice systematic way that just works for every problem you see. And the students that I've had that have transferred to the U have found all this stuff to work well. So, yeah. There are always, I always have students who are just really like tenaciously hang on to what they feel like are their methods that they learned from Physics 1. And I have to say, I really do kind of like the spirit. I kind of like fighting the man, fighting the system, but it's pretty counterproductive if you're just trying to get to the point where you can do the problems that I give you well. You know what I mean? I'm trying to give you ways that set you up to do those problems. And I'm trying to give you ways that where you're following the same steps on every problem, because that's how you solidify a set of steps so that in 6 months or a year or whatever, when a problem comes up, you have a prayer of doing it right instead of like, oh, I vaguely remember that I was sitting over by, or whatever. That was back when baggy pants were popular or whatever. Okay. And of course, if anybody has any questions about these, or if you think maybe I missed something you did for sure, and you think you should have gotten a couple more points than you did or whatever, I'd be happy to talk about that stuff. So now, does anyone have any homework problems that you would like me to go over? Anything that was tricky from the assignments? Yes.
Rigid body FPDs, question 5.
Oh, yeah. So the idea here is you have this whole list of joints, and you have 3 categories of joints in 2 dimensions. And really, it's just a matter of looking up the joint type that you have and then drawing it in your free body diagram the way that it says to do it in the table. In a way, that's not a very satisfying way to do joints. You'd like to feel like you kind of understand why that's the case. And in order to understand why a joint applies a certain set of loads, you have to think about it this way. First, think about 2 bodies that are near each other out in outer space, but not connected by joints. One of those bodies, compared to the other one, can move in 2 axes of translation, and it can move along one axis of rotation. Those are the degrees of freedom. Okay, so in 2 dimensions, a body has 3 degrees of freedom. And all a joint does is reduce those degrees of freedom. So a frictionless contact eliminates 1 degree of freedom. There's one direction that this object can't move now compared to the other one. A hinge joint between 2 bodies takes away 2 degrees of freedom. The thing can't move relative to the other body along one axis or a perpendicular axis. And so all of these joints are defined by how many of these degrees of freedom are removed from the body. Okay, so and so if you think about for each joint what degrees of freedom are removed by the joint, you can reason out what kind of loads the joint applies. And I'll try to bring that out as I do this problem. So we're on rigid body, free body diagrams. And number 5. Okay. Well, there are a few ways to do this, and some are more useful than others. So there are multiple ways to do this, and they introduce different numbers of variables. And you always want to choose the way that introduces the smallest number of variables. So if you did this another way, that's fine. You just would have more variables. For the purposes of this problem, these are all equal. But when we get to actually solving these problems, if you can figure out a way that reduces the number of variables, that's good. Because we're always in this race between variables that we're trying to solve for and equations that we have from the equations of motion, Newton's laws and stuff. And if you have more variables than equations, you're SOL, But if you can come up with as many equations as you have variables, then you have a system of equations you can solve. Okay, so the first way you could think of this, and it all just comes down to what we're choosing as our isolated body. So first I'm going to do sort of the most obvious one. I'm going to just isolate the beam. And I don't remember if it said maybe somewhere to neglect the masses, but I'm going to assume this has a mass. So I'm going to put just the weight going down. And the weight always acts at the center of mass of the object. So for these simple shapes, it's just always right at the middle. And now we'll sort of mentally go around the boundary looking for contact with the surroundings. There's a joint here. That's a pin and slot joint. So that pin in slot joint, if everything else was removed, what kind of motions? So before we start introducing joints, this thing is free to translate along X, translate along Y, and rotate around Z as staying in the plane, okay? If you have a pin that can only slide along this slot, and this thing can rotate around this slot, what of those 3 degrees of freedom, what's eliminated? That's the question. And what we can't do now is we can't translate this point perpendicular to the slot. Okay? We can't do that anymore. We could still translate parallel to the slot, and we can still rotate about the Z-axis. Okay? Translations are eliminated by applying forces. Rotations are eliminated by applying couples. And so what we know is we're applying a force to this point perpendicular to that slot. Okay, so that's how you would reason it out. Or if you don't want to reason it out, you can just, sort of memorize what the different joints do. I think a combination of those two is probably the most useful because you can sort of sanity check what the other way of thinking of it says. Okay, so perpendicular to that slot, I can draw that force direction two ways, either up or down, because there's two vectors perpendicular to that slot. I'll draw it up, but down would be perfectly fine. And when you have pin and slot joints, so I'm going to represent that with a scalar variable, just a number, and I'll call that RA. And with a pin and slot joint, your scalar variable can come out positive or negative. Remember with cable tensions, I said it has to be positive. This slot will apply a force up or down. And now we'll go over to the other one. I'll call this RB. That is a pin joint. The rule for pin joints is an unknown force vector. And so I'm just going to draw my component directions, and I'll give this the vector variable name RB. It doesn't matter what you call those variables, but it's important that that's a vector variable and this is a scalar variable. Okay, let's reason this out. Like, does it make sense that this eliminates, that this has a force component along X and along Y? Well, yeah, you can't, for each one of these joints, forget about the other stuff going on and just think about the only thing here is that pin joint. That pin joint keeps the point on that body from translating along X. It keeps it from translating along Y, but it still would allow it to rotate around the pin. And so we have two force components, but no couple. Okay, and now we have to think about, okay, so here's where it gets to be a mess. Now there's also a joint between this beam and the base of the pulley, which is a fixed joint. It's welded there. This thing can't rotate or anything. And so what's the rule for a fixed joint? We have a full unknown force vector, and it also doesn't allow rotation. So we have a couple also. So here we have a force vector. I guess it looks like it's at the midpoint. So we have a force vector here like this. I'll call that RP for pulley. And then we have a couple like this that I'll call MP. Yep.
Are pulleys always fixed joints?
Pretty much. I mean, I just, like when you think of putting a pulley on something, you fix its base to with screws or whatever. So that would be a fixed joint. But we're not going to, for the most part, if anytime you're using pulleys, you can come up with a way to have fewer variables than this. So I'm going to do a better way after this. Okay, and now we have to think about, we keep going around the boundary and we get to where the cable makes contact with the body. And so that cable is applying a force away from the body, parallel to the cable, so like that. Okay, so how many variables do we have? These are both scalars. 1, 2, this is a scalar. 3, we're assuming we know mg. So 3 variables. These are both vectors, so 2 and 2. So we have seven variables, and this is just a single rigid body. So we can't yet solve this. Okay, so this would cause us a problem. I mean, then we would go and we would isolate the pulley as a rigid body. We could use that to get three more variables. I mean, three more equations. But this is not the simplest way to do this problem. So instead, what I'm going to do is I'm going to isolate this. Okay.
Basically, just include that as all of it.
Yeah, then like depending on what you choose as your free body, then a lot of stuff that was external loads in another way of looking at it becomes internal loads and you can skip it.
Yeah.
Okay. So notice that all this tension stuff going on in this almost horizontal part of the cable isn't there anymore. And this contact between the base of the pulley and the beam is not there anymore. So this is gonna be simpler. So free body diagram, second approach. Let's see. So we have the beam, and then we have something like that. Okay. Most of this stuff stays the same. So this will still be RA. Oh, there's still the weight force mg down. This is still an unknown force vector RB. But now the couple and this RP applied by the base of the pulley, we don't have to worry about those. The only other place where the surroundings make contact with the boundary are where the excluded cable contacts the included cable. And so that's parallel to the cable, away from the body. So like that. Well, we still can't solve that. Still too many variables, but this had 7 variables. This has 4 variables. The reason we can't solve it, by the way, like if you just look at it, it's over constrained. This thing would be stable without that cable there, or without that pin and slot joint there. If you built this thing, nothing would blow up. You know, it's like perfectly valid. I mean, I don't know, but it doesn't violate any laws of nature or anything. So it's kind of unsatisfying that you can't calculate a solution for that. Well, you can calculate a solution. It just depends on the microscopic deformations of the materials. And that's something that when you take deformable body mechanics, you'll talk about how to calculate statically indeterminate systems. That's what this is. We can't solve it just using statics, but you can solve it. Any questions about this one? Yes.
What if we included the rest of the string? Would that be good?
At some point, you still have to close your boundary, and then so if you included all of the rest of the string and nothing else, then you would still have the ceiling pulling on the string, and you'd have to include that. And if you said like, okay, I'm going to go do all of the string and then a little chunk of the ceiling, then you'd have all of the string, and then you'd have a fixed joint between your included part of the ceiling and the excluded part of the ceiling. So there's no way around that. That's a good question. At some point, you have to close your outline. Any other questions? Okay, any other homework questions you'd like me to go over? All right, well, let's do some rigid bodies. Let's do some examples. So, really what we're going to do is start out with free body diagrams like this, and then we're going to do the calculations. And I'm going to do all of these by filling out all of my forces and moments in a table. I think that table is a really nice way to organize stuff. It's something you can look back to. If you have a mistake, you have it all written out there, you know. I think you'll like it if you get used to using it. So let's say that we have a hinge connected to the wall. And let's say that this bar makes an angle of 20 degrees with the vertical. And then this end of the bar makes frictionless contact. So no friction. And then at the midpoint of the bar, we have a force going to the left of 100 newtons. And let's say that the mass of this bar is 5 kilograms. And we want to calculate the reaction loads. I'm going to start out with the free body diagram of the bar. So it was 5, right? So this is 49.05 for the weight. And then we have the 100 that's given. And now we have to deal with those two joints. Up here at the pin joint or the hinge joint, that restricts translation along X and Y. So that's a full unknown force vector, but it doesn't eliminate rotation, so there's no couple. So we have a full unknown force vector I'll call RA. And then down here, this is a frictionless contact. The rules for a frictionless contact are, well, we did frictionless contacts with particle statics. This is perpendicular to the surface toward the chosen body. So if the surface is like that, the force is perpendicular to the surface toward the chosen body. Give it whatever name you want. You could call it RB or N or whatever. And so that's a complete free body diagram. when we're doing two-dimensional problems like this, how many variables can you have? Yeah, that's right. 3. You can only deal with 3 variables if you're in 2 dimensions, because you only have 3 degrees of freedom and you only have 3 Newton's laws. You have X and Y for Newton's second law, and you have 1 component of the moment equation, rotational Newton's second law. Okay, so I'm going to write out a table. So my first column is rho, my second one is force, my third one is the moment. You might, in solutions, at least sometimes in the solutions, you might see 2 columns before the rho vector, a P column and an A column. Well, you can always calculate the coordinates where the force is applied, the coordinates of the about point, and subtract them. I used to do it with 5 columns in here. I don't do that anymore. You just need to remember the definition of that rho vector. Okay, so remember that the rho vector is the vector from the about point to the force where the force is applied. Okay, so I'm going to start out with RA, and since the rho vector is from the about point to where the force is applied, we have to choose an about point for this calculation. What do we want to choose? It doesn't matter. If you choose a point where you have the most unknown forces, it simplifies the math a little, but it doesn't really matter. You can just use reduced row echelon form to solve this anyways. I guess I'll choose my about point here. Ben, you were asking before, like, differences between dynamics and statics. This is a place where, you know, in dynamics, you have to be very particular about your about point. Your only options are the center of mass of the body or a fixed point. In statics, because everything is a fixed point, nothing's moving, you can put your about point anywhere you want on the whole problem. On the body, off the body, you know, you could put your about point a mile that way if you wanted, and everything would work out just as well. Okay. Okay, so what the rho vector for this force RA, that is a vector from our about point, which is the red dot, to where this force RA is applied. What is that rho vector? It's kind of like a trick question or something. They're the same point, so that vector is 0. Oh, what happened?
Is the benefit of choosing where the most unknowns are?
That is right. That is right, because then you don't have any moment for that force.
How long is the
2 meters. Okay, so the rho vector is zeros. The force vector is RAX, RAY. The cross product is this times this minus this times this. Gives you a z component because we're in the xy plane. And so you get 0 here for the moment. So yeah, that's the benefit of putting the about point where you have the most unknowns. But now we have to keep that about point for all the other forces. Okay, so now what about this 100 Newton force? So from the red dot, the about point, to the center of this beam, the whole thing is 2 meters. So to here is a length of 1 meter. So we have 1 meter times cosine and sine of negative 70. So this is 0.342, negative 0.940. That force vector is negative 100, 0. The cross product is this times this minus this times this. So that is negative 94.0. Yes?
Can I ask where you got the negative 70 degrees from?
Yeah.
Oh, okay.
And now we'll go to the 49.05. Oh no. What are you doing? Man, you know, when I first started here, I had a computer that it didn't have touch sensitivity. It just had a stylus. It never stopped working. It was great. And now, like, as technology gets better and better, I have more and more crashes.
Complexity getting higher. And
Yeah.
More fail points.
Right,
Yeah.
right. So, okay, the next one is 49.05. This force is applied at the same spot. So that means that the rho vector is the same as for the 100. The force vector is 0, negative 49.05. Cross product is this times this, minus this times this. And that gives negative 16.775. And then last is the normal force N. That is 2 times cosine and sine of negative 70 degrees. So that's just doubling both of these components. So this is 0.684, negative 1.880. That force vector is straight up, so this is 0n. Cross product is this times this, minus this times this, so that is 0.684n. Okay, now we have all of the forces for Newton's second law here, all the moments for rotational Newton's second law there. And if you need to go back and check something, you have it all right in front of you, how you did that calculation. You're going to like having this there. So Newton's second law says RAX, RAY plus negative 100, 0, plus 0, negative 49.05, plus 0n is equal to zeros. And then the moment equation, rotational Newton's second law, says negative 94.0 minus 16.775 plus 0.684n is equal to 0. And so N is equal to 161.95 newtons. And then RA, plug N in to the Y equation where you need it. RA, the X component is positive 100. The Y component is negative 145.18. So there's the maybe slightly surprising fact that in order to have this in equilibrium with the conditions that we have, this actually has to pull down on the left side. You know, sometimes you'll get sort of surprising stuff like that. Let's also think about these. Let's think about the meanings of these moments. We chose our about point to be here. Okay, so the signs of those moments, and we're still in 2D, so these are Z components of moments that are listed under the moment column. The signs will tell you whether it's clockwise or counterclockwise, the rotation that this force would produce. So one by one, just isolate the one force you're thinking of. Think of this as the hinge that it can rotate around, and think about whether those forces would produce a clockwise or a counterclockwise rotation. Okay? Positive means counterclockwise, negative means clockwise. So this 100, would that get rid of all the other stuff, would this 100 make it rotate clockwise or counterclockwise around A? You know, if you took a little hammer and imagine this in space, you know, so there's no gravity, give it a little tap this way, it would make this thing rotate clockwise. And you can see that we have a negative moment because of that, a negative Z component of the moment. Okay, the 49.05, again, this one's a little harder to visualize, but tap it, it would make it rotate this way. And you see that, that it's negative. And now what about this N? If everything else is gone, you tap it this way, it would make it rotate counterclockwise. And so that moment you get there is positive. Yep.
Just like a random question, but like approximately the mg value,
Yeah.
it is half of the 100 approximately.
Yeah.
But the moment it's like completely far off. Is there a reason why it's not like just approximately half?
Yeah, it is. It's because, I mean, yeah, it's because there's a much bigger moment arm for this thing vertically than there is horizontally. You know, since this is only at a 20-degree angle. And so both of these are at the midpoint, but horizontally, it's much closer to the about point than it is vertically. So that 100 Newton force has a really big moment arm. You know, think of the wrench turning the screw, the bolt. That was in the lecture video, right? There's a picture of a wrench and that moment arm is like how far out on the wrench you're pushing to try to turn this bolt. Okay. This 100 Newton force has a big piece of the wrench in order to turn this body. The horizontal force has a very short piece of wrench, just this right here. So that's why. Any other questions about that problem? Okay. Let's do one with a fixed joint. So let's say that we have a cantilever beam. So sticking out from the wall this way. And we have a 30 Newton force at the midpoint and a 30 Newton force at the end point. And the length of this is 1 meter. And the mass is 4 kilograms. And we want to calculate the reaction loads at the wall. Okay, so start with a free body diagram. We have a weight force at the center of 4 times 9.81, so that's 39.24 newtons. We have a 30 Newton force there and a 30 Newton force here. And then the only other place that the body contacts its surroundings is at the wall. So what kind of loads are applied to a body by a fixed joint? So you can sort of memorize that, which is probably for the best anyways, and or you can think about the degrees of freedom that are eliminated. This doesn't allow a horizontal motion translation. It doesn't allow a vertical translation, and it doesn't allow a rotation if that's like welded. So we have 2 components of a force and a couple. So I'll draw the unknown force vector this way. I'll call that force vector R. And then I'll draw my couple like this, and I'll call that reaction moment, M sub R. And then my table, rho, force, moment. I'll put my about point here. Again, it simplifies the math a little, but doesn't matter. You can still, no matter where you put it, if you can solve it with the about point in one place, you can solve it any other place. Okay, so I'll start with the, well, I guess I'll start with the stuff at the about point. So this R force, what is the vector from the about point to where R is applied? 0, yep. And the force vector is Rx, Ry. Cross product is 0. Now I'll do the couple, Mr. Well, couples, remember that couples are an interesting thing. They do not depend on the about point. The moment of a couple does not change as the about point changes. Also, couples are equal and opposite forces, so they don't have a net force. Their force adds up to 0. So we can always just cross these out. We don't care about those. And this is just going to be M sub R in the moment. Then I'll go to the 30 at the midpoint. This whole thing has a length of 1 meter. So the row vector, the vector from the about point to that force, is negative 0.50. The force vector is in the negative y direction, 0, negative 30. Cross product is this times this minus this times this. So that's 15. Then we have the weight force. Since that's at the same point as this 30 we just did, it has the same row vector. The force is 0, negative 39.24. The cross product is this times this minus this times this. So that is positive 19.62. One, two, three, four. 1, 2, 3, 4, 5. So we still just have one more to do. So this is the 30 on the left. The row vector is negative 1, 0. The force is 0, negative 30. The cross product is 30. And so Newton's second law, we're just going to add up all the forces in the force column, set it equal to 0. So we have Rx, Ry plus 0, negative 30. Plus 0, negative 39.24. Plus 0, negative 30 is equal to zeros. And right away we can calculate that R is equal to 0 for X and positive 99.24 for Y. And then we'll go to the moment equation. Add up everything in the moment column. So we have MR plus 15 plus 19.62 plus 30 is equal to 0. So MR is equal to, I think that's 64.62 negative. And the units are Newton meters. Okay, so you might have kind of a rough intuition about what a Newton is. I mean, it's about 4 newtons to a pound. So, that's about 25 pounds of force that the wall is applying to the right end of the beam. What about that couple? Do you have any intuition about couples? I think people who do a lot of engine work or whatever probably are more better at imagining couples in inch pounds, or that's what it is, right? Inch pounds. The more common, like torque wrenches or whatever. But okay, so let's try to wrap our head around it. So first of all, let's think about the sign of this couple. Does it make sense that the wall has to apply a negative couple to this beam? Well, all of these externally applied forces are trying to make this beam rotate counterclockwise. And so we would expect that the wall has to apply a counteracting moment that's clockwise. So the negative makes sense. How big a couple is that? Is that like, enough to rotate the sun, or, a Newton meter couple, if you have a good diameter screwdriver and you're really trying to twist the screwdriver as hard as you can probably generate with one hand about 10 Newton meters of torque. So, that's on the same rough order of magnitude as what you could really work to produce with a screwdriver. A little bigger. Anybody have any questions about that? Yes.
I was gonna say that it's like if you exerted 64.62 newtons over 1 meter. That's what that means.
Yes, that means that's right. If the moment arm, so if you had a wrench that was 1 meter long, so that's a very long wrench, this long a wrench. But imagine a 1 meter long wrench. That is the force in newtons that you would have to apply. That's a nice way to think about it. Yes.
Just one question. I think on the beam free body diagram, for the couple part.
Yeah.
You wrote they're rotating counterclockwise.
Right.
Is there how do you determine?
Okay. Yes. So this sign convention can get confusing to people. So just like when you draw your unknown force vectors, you draw them in the positive x and positive y directions. Okay. With couples, draw them in the direction of a positive moment. What that means is if you get a positive answer, this is the direction it's in. If you get a negative answer, it's in the opposite direction.
So you just correct it once we solve the problem.
Well, it's
right.
Yeah, and it's showing it's an unknown force.
Okay. Yeah, so
those are unknown forces, and it's just showing you what the positive direction for.
Yeah, so think of this. So this means the exact same thing as this.
Right.
Yeah. So like when you calculate your currents or whatever, like if you assume a certain current direction and then you get a negative answer, it means your number is right, but the direction was opposite. Any other questions? Okay, well, I'm going to give you some three-dimensional stuff to watch a video on and some more of these problems. And, over the next sort of pretty much 2 full weeks, we'll just be making sense out of this and then applying it to collections of bodies, structures. Okay, that's all.